Welcome to Pomodoro Joe for Friday, April 7th, 2023. Today we're doing LeetCode problem 1020, number of enclaves. This is a medium problem. So you are given an m by n binary matrix grid, where 0 represents a C cell and 1 represents a land cell. A move consists of walking from one land cell to another adjacent, forward directionally, land cell, or walking off the boundary of the grid. Return the number of land cells in the grid for which we cannot walk off the boundary of the grid in any number of moves. All right, and then we have some examples. So we can't walk off the boundary from these cells, but we can from this cell. So there's 3 total. Yep. This is remarkably similar to yesterday's problem, which is LeetCode, let's see, 1254, number of closed islands. This is nearly identical. So if you checked out that video, this one should be a piece of cake. All right, so we'll put 25 minutes on the Pomodoro timer and get started. So the plan here is to do a grid traversal. So we will go through every cell in order, looking for a land cell. As soon as we find a land cell, then we will start going through a grid type traversal, where we'll check the cell and we'll check all the surrounding cells for adjacent land. Then we'll follow all the adjacent land cells until we either find that we've run out of adjacent land cells or until we reach an edge. All right, so with any grid traversal type problem, there's a couple basic things that we'll need. First thing that we're going to need here is our result. It will set to 0, and we will return our result at the end. The other thing we're going to need is we'll have to keep track of which cells we've already traversed. So we'll keep a visited set. And finally, we'll need some queue of cells to go through, but we'll come back to that. I think I'll actually break this down into a sub function to help us out. So let's have some, well, we'll come back to this. We'll keep going. Okay, so I think I will want some helper variables here. Let's create a couple helper variables. I'd like to know how large my grid is. So we'll have a max x, and that's going to be the length of our grid for our first row. So that'll be length of grid 0. It's actually going to be length of grid 0 minus 1. I want this to match the index of the last element in this row. And then let's see, we'll have a max y, and that's going to be the length of our grid. And again, we'll do minus 1. So that we can keep track of the last row, the index of the last row. Okay, so now that I have my max x and my max y, we can start going through all of our cells. So for x in range, max x, and we actually do have to add the 1 back here because we want to go all the way to the end, and range is exclusive, meaning it does not include the last element. And then for y in range, and this will be max y plus 1. So this basically gives us every combination of x and y. So that's going to traverse every cell in our grid. And at this point, we'll just have some function that's going to help us out. So our result, we'll say it was plus equal, I guess what we'll call this is cells in enclave. Okay, I'll call it cells in enclave at. I don't really like that name either. I'll just do a cell count. And we're going to have some start x and y. Or maybe I'll just call it enclave. There we go. Cool. Naming is one of the hardest things to do. Okay, so now we have this enclave count. So we'll be going through every single cell in our grid, and we'll say if this, maybe I should do that first. Yeah, let's do that. Let's make it a little bit easier on ourselves. We only need to check to see if this is an enclave, if this cell is land to begin with. So we'll say if our grid at this y x is equal to 1, then we'll do this. So we're going to check if it's a land before we even bother calling this enclave count. Now, one thing that I will point out, so it might seem strange to be doing grid y, x. Well, that's because I'm choosing a coordinate system that's like a screen space type coordinate system, where my 0, 0 is in the top left corner, and x will increase as we go to the right, and y will increase as we go down. So 0, 0 is up here, y increases down, and x increases across. So the reason why y then becomes our first argument is because y represents the row. So this is row 0, so that's y 0. Then as we go down, our y increases, so this is row 1, and that's y1. Then this is y2 and y3. So our first index into our grid will be the row, and the second index will be the column. All right, so we have to do grid yx. So if grid yx is equal to 1, then we know we have some land, and this might be an enclave. So we'll check to see if it's an enclave, and we'll add that to our result. Okay, so then checking the enclave. So we're going to start with some, I'll call this start x and start y. So this is just the land where we'll start. This one will have its own result. So I'll call it count. And we'll start it to 0, and then we'll return count at the end. All right, so now in this one, we'll have to do a little bit of a different type of traversals. So internally here, we'll be doing a different type of traversal. This is more of a depth-first search type traversal. In fact, this is more like a breadth-first search type traversal. Well, we'll look at our current cell, then we'll check out all the 4 surrounding cells, up, down, left, and right, and we'll keep either recursing or pushing them on the stack and popping them off the stack. Personally, I like the stack option or the queue option, so I'm going with that. So we'll have some queue. And in our queue, it's just a list. We'll have elements that will be our x, y coordinates. So this one's going to be start x and start y. So every time we go through our loop, we'll be grabbing one element out of the queue, checking to see if we have adjacent land cells. If we do, we'll push those land cells into the queue. And then when we continue our loop, we'll pop those land cells out of our queue. So you can think of this queue as just a way to remember, hey, which land cells do we still need to check? Or which coordinates do we still need to check? So we're going to start by saying, well, we need to check our start coordinates. And so while we still have something in our queue, we'll pop our cell out of the queue. Now I'm going to pop the first cell, so cell at index 0. This is going to represent a breadth-first search. You could pop at -1, which would be a depth-first search, but I think breadth-first will be our best bet. It's kind of a judgment call. They both will get the job done, but sometimes a breadth-first, I'm guessing in this case, a breadth-first will be a little bit faster. All right, so we pop our cell out of the queue. Now we can get our, in fact, I don't need to do this. I could say pop x, y out of the queue. That way it sort of unwraps our tuple for us. So we grab our x, y out of the queue. Now we want to check, I guess, a couple things. Is this cell land? And also, have we visited this cell? So first we'll check if it's land. Actually, no, let's check if it's visited. Let's do that first. So if our x, y is in our visited, so we've already been to this cell before, we don't actually need to process it, so we'll just continue. The next thing we'll check, is this a water cell? If it's water, then we don't need to bother processing. So let's see, we'll have to check our grid again at y first and then x. So if this is equal to 0, meaning a water cell, then we'll just continue. Let's see. And someplace in between, I'm going to add this to our visited list. So we're grabbing some coordinates out of our queue, checking to see if we've already visited this cell. If we haven't, then I want to make sure that I record that we're visiting this cell now. So I'll say visited. add, and we'll be adding a tuple of x, y. All right. So now we've checked if we've visited, we've added it to our visited list, and we've checked to see if it's C. So at this point, we know we have a land cell that we have not yet visited. So let's see. I think what I want to do here is first check to see, is this land cell connected to our edge? Because that's the one thing that I'm looking for. If we're not connected to the boundary, then we'll keep going. If we are connected to the boundary, I need to record that we're connected to the boundary. So I think I'll need another piece of information here. Let's see. I'll have it, let's see, yeah, is connected to boundary. And I'll set it to false to begin with. So this is just going to tell us whether or not our land, not necessarily this cell, but this cell and all the adjacent or connected land cells, if any of them are connected to a boundary. So let's check that now. Are we connected to a boundary? All right, so how do we know if we're connected to a boundary? Well, we just have to look at our x and y coordinate. So if our x coordinate is 0, that means we're connected to this leftmost boundary. Or if our x coordinate is equal to the max x, that means we are at this rightmost boundary. Or if our y is 0, which means we're at the top, or if our y is equal to max y, then we're at the bottom. If any of these is true, then we're on a boundary, and we have to record this by saying is connected to boundary is true. All right, so now that I know that I am checking to see if I'm on a boundary, that means when I do my return here, I only want to return the count if I'm not connected to the boundary. Because what we're looking for are these enclaves, so pieces of land that are not connected to a boundary. So I'll return count if is connected to boundary is equal to false. Otherwise, I'm going to return 0. This land was connected to a boundary, so it doesn't count as an enclave. All right, now we get to the hard part where we have to not recurse, but we have to find which cells to go to next. So at this point, we've evaluated our current cell. We've checked if it's on a boundary. Where do we go next? Well, we have to look up, down, left, and right. So I'll have some up, down, left, and right. So up will be, well, the x is going to be the same, but our y is going to be y, in this case, -1, because if you remember, my up direction is negative y, and positive y is in the down direction. All right, so, but we only want to do this if y is greater than 0. Otherwise, we're at the edge and we would go off the edge if we went any further. So we'll say our up is x, y -1 if y greater than 0. Otherwise, we don't have an up. And down will be similar. So it'll be x, but it'll be y +1. But only if y is less than our max y, else there is no up. And then we do left and right. Okay, so this should give us our up, down, left, and right coordinates, or none if you can't go in that direction. All right, just double check here. I think this is good. Now, one thing I will say is, if you do this enough, you'll find your own way of doing this. This is how I like to do it. I like to have explicit up, down, left, and rights. It takes a little bit longer. Our algorithm will not be as fast as other potential algorithms, but I think it's clear what we're doing, so I like doing it this way. But if you look at other people, they'll do this in many different ways. I recommend practicing this type of problem, do it a bunch of times, figure out the way that you like doing it. And then anytime you come up to a grid type traversal problem, you'll just have your go-to template and you can just do it without having to think. All right, so now that I have my up, down, left, and right, I like to call this my options. These are my options, and I'll just put them, say, up, down, left, and right. So these are all the options that I have. Then I'll say for every option in my options list, if that option isn't none, because remember, some of these will be none, but if the option isn't none, well, then we can add it to our queue. So now we just say This is some land. It's some land that we haven't yet been to. So I'm going to append this to my queue. And again, this is going to be a tuple, and we have to get our option at index 0, and then our option at index 1. Now, one thing I can do here to speed this up maybe a little bit, I can say if this option isn't none, and if it's not invisited. But at this point, we'll start with the basics. All right, so this is our potential option, some land either up, down, left, or right. I'm not checking to see if its value is 1. I'm not checking to see if it's ocean. I'm just saying this is some grid cell that we're connected to. So we're going to put it in our queue, and we'll handle all the visited, and if it's water, all that stuff's going to be handled up here. So we don't need to worry about it. Okay, and I think that should do it. I guess there's one thing I'm not doing. I'm not incrementing my count. So I need to keep track of all these land cells. So let's see. If we're in here, that means we have land. So we'll say count plus equals 1. So if this is true, it's water, and we'll continue. If it's not true, then this is some land, and we can add to our count. Okay, let's give this a shot and see if it works. Options is not defined. Let's see. For options in options, plural, of course. Gotta have typos. Okay, it seems to work. Let's see if we can pass all the tests. And we pass. We do a terrible job, but we pass. So we only get 5.4% for runtime and 75% for memory. So that is pretty awful. All right, let's try a couple of our speed up techniques here. So one thing, as I mentioned, we're checking to see if we have the option, but we're not checking to see what that option is, if it's water or if it's land or if it's already been visited. So one thing I'll do here, instead of saying for option in options, we'll call this, I can't call it X and Y, or I could, but I think that would be confusing. So I'll call it I and J. Oh, but that won't work either because this could be none. So I do need to call this option. So if option isn't none and option index 0, option index 1, not in visited. All right, so now we're going to check here if it's in visited and only add it to the queue if we haven't visited this cell already. That should save us a little bit, but I'm not pinning any hopes on this one. All right, boost us about 1%, so not a great score. Okay, so one other thing, well, there are a couple other things we could be doing. I mean, as you can see, there's a lot going on in here. We could be doing some things to clean this up. Again, I like having it this way only because it's very clear that we're going up, down, left, and right. Instead of using a set here, we could actually use the grid itself. So this is something I tend to avoid doing. I think it's generally bad programming practice to modify the input unless you're explicitly told you're supposed to, or you make it explicitly clear that you're going to. Because otherwise, somebody could be passing you some grid. They say, hey, use this to do whatever calculations you need, but I need it back to do some other things. If you're modifying this grid in here, that information is lost. So it's generally not a good practice to modify the inputs. However, if we want to boost our score, we might have to do that. Okay, so let's give it a shot. So here in this visited, we just have a set. We're adding things to the set. What we could do is instead of adding things to the set, we could say, this is our grid. Tell you what, first I'll make a copy. Let's do it this way. So the grid is an array of array or list of lists, which means that we can't just do a simple grid.copy. If we do this, this is what is called a shallow copy, meaning it will copy all of the first set of lists, but all the internal lists will not be copied. They'll be referenced, which means that we will be modifying our input if we did something like this. So what we really want to do is call a deep copy on our grid. Okay, and now inside here, let's make a couple helper functions. We'll call it isVisited, and pass in x and y, and we'll just return, for now, actually let me do this one step at a time. We don't have a lot of time left, but let me do it this way. So I'm not going to make any changes to how our visited works. I'm just going to change some function calls to use those in place of directly accessing visited. All right, we have two new functions. IsVisited takes x and y and checks to see if it's in visited. And we have visit taking an x and a y, and it's going to add it to our visited. So down here, when we did, let's see, visit add, and if this is in visited, so we're going to change these to say, instead of if x and y is in visited, we'll check if is visited x, y. And instead of just doing a direct add, we'll say visit. All right. And then down here, same thing, although this one didn't save us that much, so let's not even bother with this one. All right, let's see if this still works. This should still work. We're just replacing our direct access of visit with function calls. I need to remove these parentheses. Okay, let's see. And I need to add parentheses. So many errors. I feel the time pressure, so I'm making mistakes. Okay, so this still works. This shouldn't actually save us anything at this point. This might even take more time because we're doing function calls. So let's just check. It's about the same. But let's see, if we replace this visited, instead of using a set, let's do a deep copy of our grid. Now in here, instead of saying if it's in visited, we'll just check to see if our visited, at this, again, it's going to be y first and x. If this is equal to 0, meaning it's ocean, or we're going to use 0, meaning visited. So if it's visited or ocean, we return true. Otherwise, we'll say visited at our y, x is equal to 0. That becomes our visited representation. Okay, let's see if this still works. Okay, that still works. Now, let's see if this saves us anything. Instead of using a set, we're using a grid. Makes 0 difference. 5% as opposed to, what was it before? 5.4, 5.2, yeah. Virtually 0 difference. But now if we don't do the copy of our grid, and we just use the grid directly, again, I do not recommend doing this. Oh, and it doesn't work. That actually surprises me. So in that case, this might not actually help us. I wonder what I'm missing. I'm surprised by this. I could have sworn this would work. Oh, I think it's this. That's why. We were doing a double check essentially on the grid equals 0. Okay. Okay, this works. With 1 minute left, let's see if we can get over 10%. I'm really pushing it on this one. And we do. Now we're at 14% for runtime and 90% for memory, but we are modifying our input grid, which I do not recommend. So check this one out, see if you can do better. I'm sure you can, because 14% is such a low score. So yeah, hope you enjoyed this, hope you learned something, hope you had fun, hope you can go out and write better code.